We are in chapter 5 is on shear. This is the 42nd session overall, and here we'll discuss an example on shear center and several examples on shear stress involving unsymmetric cases. Here we have a glimpse of the sessions covered in the first 4 chapters. This is the last session of the 5th chapter where we have been discussing shear. In the last 2 sessions, we have been dealing with unsymmetrical cases, and here we look at some shear stress examples for such cases. We find the shear center for this semicircle of thickness T. If a load acts vertically upwards to the shear center, then the shear flow and the corresponding shear forces acting on this section will be downwards. We consider that to be the case. Here, to find the moment of inertia, we use the parallel axis theorem, and we have to integrate unlike the cases we have dealt with so far. Consider this small element which subtends an angle d phi. Let r be the radius of the center line and the thickness be d. Then this distance is r d phi. The area of this portion is T r d phi. The vertical distance of this element from the neutral axis is r cos phi. So using the parallel axis theorem, we get the moment of inertia of the element as AD square. So this is A, and we square this and we get this expression. IZZ is obtained by integrating from 0 to pi by 2 and then multiplying by 2 for the two portions. Cos square phi can be written as cos 2 phi plus 1 divided by 2. This 2 and this 2 cancel. We get this expression which we can write as two separate integrals. Integrating cos 2 phi, we get sin 2 phi divided by 2. Substituting the limit pi by 2, we get sin pi, which is 0, and sin 0, which is also 0. For this portion, we substitute pi by 2 to get pi r cubed d by 2. So when we substitute 0, we get 0. So IZZ is given by this expression. Consider this small area, then the total area is r d phi into t, and the distance from the neutral axis is r cos phi. So this is the Q for this small element. We'll find out the shear stress acting at an angle theta. So to find Q, we integrate from 0 to theta. Integrating and substituting the limits, we get this expression. So at theta is equal to pi by 2, this is the expression. We have just found the tau S acting. Like earlier, we'll find the force acting on an infinitesimal area. After that, we'll find the moment acting to that force. So here, if tau S is acting, then we have the force as tau S dA, and if you want the moment, then we have tau S dA into R. So we have found the moment for an infinitesimal force. Here we have considered tau as at an angle phi. So we substitute this expression here. Theta is phi here. The area dA is dr d phi. So we get this expression for t m0. We can get the total moment acting about O by integrating from 0 to pi. Integrating sine phi, we get minus cos phi. If we substitute the limit pi here, then we get plus 2VR by pi. And considering this limit, we get minus into minus 2VR by pi. So on the whole, we get 4VR divided by pi. We have been finding the shear center by considering forces in a section and finding out the point where the moment of the forces is 0. Another way to find the shear center is to take any point O, then the moment due to the external force at that point will be negated by the moment due to the forces acting in the section. This is the case we just discussed, and we can check what we just mentioned. Here, this whole force is V, the external force is V, the horizontal force is 0.235 p, and this is the distance of the shear center that we determined earlier. So we consider moment about point O. Then F1h multiplied by 100 plus V into 50 is equal to V into E plus 50. We can see here that the left and right hand side match each other. Here we have used this method to find the distance of the shear center. We have taken moment about the point O. So the force V into this distance is equal to 4VR divided by pi, from which we get E is equal to 1.27 R. Here we find the variation of stress in this section. If a vertical load acting upwards is applied at the shear center, then the shear flow and the corresponding shear forces in the section will be directed as shown. The moment of inertia is given here. It can be found in a straightforward way. We next find the force F1. As we have earlier seen, for a small element of a distance from the edge, the force acting with tau is T into ds. To find the force F1, we integrate from 0 to 45. If the distance from the edge is z, then the statical moment is 8 into z into 70, which is the distance from the neutral axis. We integrate and we substitute the limits, and also Izz to get F1. We can similarly find the force F2. If a small element is taken at a distance from the edge, and the force again is tau s E into ds. We integrate from 0 to 45 to find the force F2. Q here is 6 into Z, and the distance from the neutral axis is 20. Integrating and substituting the limits and also I, we get F. We can now find the position of the shear center. So F1 into 140 plus F2 into 40 would be equal to V into E, from which we find E. In order to find the stress variation, we find the stress at B, B, and E. Since the point B is a junction, we find the stress just above the point D, just below the point D, and just to the right. Stress at B is given as VQ by IB. Q here is 8 into 45 into 70. Substituting the other values, we get the stress at B. To get the stress just above B, we use the Q that we have already determined of the horizontal portion and also the Q of this vertical portion. So the Q of the vertical portion is 8 into 50 into the distance, which is 45. Substituting other values, we get the stress just above B. The stress right to B is due to this arm. So Q is 6 into 45 and the distance of the centroid is 20. So substituting the other values, we get this stress. Get the stress just below D, we add the Q that we have found out for this arm and for this vertical portion and also this arm. So we have added the 3 portions. And substituting the other values, we get the stress. As we turn here, we notice that the shear flow remains the same. So the stress of 7.26 over 6 millimeter becomes 5.445 over 8 millimeter. If we add this stress to the stress just above D, we get the stress just below D. To get the stress at E, we use the Q that we have obtained earlier plus the Q of this portion, which is 8 into 20 and the distance is 10. We substitute the values and we get the stress at E. The stresses has been plotted here. The tau xz stresses vary linearly and the tau xy stresses varies in a parabolic manner. At D, this is the stress just above and this is the stress just below. If a vertical applied force does not pass through the shear center, then the section will be subjected to stresses both due to shear and torque. Here a force aligned with the middle of the web acts. So this force will create both a shear and a torque in this section. We can find out the maximum shear stress acting on the section. We'll use earlier determined methods of finding stresses in thin wall sections. To start with, we find IZZ this section. We need the position of the shear center to find out the torque applied on the section. For this section, this distance is given by this formula. So we have found out the distance. So the torque applied in the section would be this 17 kilonewton multiplied by E. So we get this as the torque. We next find out the maximum shear stress acting due to the shear force. This will be at the neutral axis. So we use PQ by IT. Q is of this horizontal portion and this vertical portion here. Substituting other values, we get the maximum shear stress due to the shear. To find out shear stress due to torque, this whole C section is considered to be a rectangle. The maximum shear stress is considered to occur at the center of the wider face, so it will occur along the neutral axis. Tau max for torsion is given by this formula. Here A is 40 plus 120 plus 40, so 200. B is 6. A by B is greater than 5, so we can use this formula. We find C1. We then substitute the values we have earlier obtained the torque to get the maximum stress due to torque. Maximum shear stress will be on the side where the two stresses add up. So we find tau max total. The force shown here and in the next problem is considered to be the internal force acting on the section. We now look at sections with no axis of symmetry and find out the stresses. This is a Z section which does not have an axis of symmetry. Point C is the center of symmetry and also the shear center. The load here is applied so that it passes through this point. As such, there would be no torque acting on the section. For such a section with no axis of symmetry, we need to find out the principal centroidal axis first. The load here is not aligned with any of the principal centroidal axis, so we have to take components of the load which aligns with the principal centroidal axis. We then carry out our analysis to find stresses. To start with, we take an arbitrary axis, a y and a z axis. We find out Iy, Iz, and also Iyz, which can be determined using a formula. With Iy, Iz, and Iyz obtained, we can find out tan 2 theta. So here we find out tan 2 theta and then 2 theta and theta, first in radians and then in degrees. So the principal centroidal axis is 31.85 degrees counterclockwise to the y-axis. Similarly, the other principal centroidal axis is at a same angle counterclockwise to the z-axis. We denote these two axes as y dash and z dash. We can now find out I y dash and I z dash. I y dash can be found using this formula, where we know I y, I z, and eta. Similarly, I z dash can be found using this formula. So we have determined I y dash and I z dash. Here we have resolved the forces along the two principal centroidal axes. We'll find out the stresses due to these two forces in turn. First, we deal with this force. So if this is the internal force, then this will be the direction of the shear flow. We'll find out the stresses from A to B and B to C. To find out the stresses from A to B, we consider a portion from the free edge as earlier. So let the length of this portion be S. Then this angle is 31.85 and this distance is sine 31.85 into S, which is 0.528 S. This angle is 58.15. So the vertical distance between B to C is 75 into sine 58.15. And the vertical distance from A to B is 100 into sine 31.85. So the total vertical distance from A is the sum of these two distances, which is 116.48. The distance of the centroid of this section from the neutral axis is 116.48 minus half of this, which is 0.264 S. Tau S is VQ by IT. Q here is S into P into this distance, which we can see here. P is this force and I is I y dash, which we have found earlier. So here we get an expression of tau S between A and B. At B, S is 100 and we find tau B to be 13.619 MPa. We now determine the stress between B and C. As earlier, we considered a portion of length S. Then this angle is 58.15 degrees and sine of that angle is 0.8494. So this vertical distance is 0.8494 S. We earlier found vertical distance between B and C as 63.71. So the distance from the centroid of this section to the neutral axis is 63.71 minus 0.4247 S. So the shear stress between B and C would be tau P plus the shear stress considering the Q of this portion. Q of this portion is S into P into this distance. Here again, V is this value and I is I y dash. So we get tau S in B to C as given by this expression. At C, S is 75, so we get tau C as equal to 17.23 MPa. Here we consider the other load is perpendicular to the z-axis and find out the stresses in the section. We find out the stresses between A and B and then B and C. For this internal load, this would be the variation of the shear flow. We take a section from the free end of length S. Then, since the sine of this angle is 0.8494, this vertical distance is 0.8494 s. We now find the distance of this neutral axis from the point A. AB is 100 millimeter, so this distance is 100 into sine of this angle, it is 84.94. Now BC is 75, this angle is 31.85. So this distance is 75 into sine 31.85, that is 39.58. So the vertical distance of the neutral axis from the point A is 45.36. So this distance is 45.36. The distance of the centroid of this section from the neutral axis is 45.36 minus half of this, that is 0.4247 s. The shear stress tau s is Vq divided by IT. Q is S into T into this distance, which is given here. V is this load and I is IZ dash that we calculated earlier. So tau S is given by this expression. At B, S is 100 and tau B2 is 2.537 MPa. The direction of the shear stress, the shear flow in BC and BA are not the same. Till now, with all the cases we have dealt with, the direction of the shear flow had been the same. As earlier, we take a section and we find out Q and the shear stress and add this stress. Over here, because the direction is different, the stress is added as minus tau P2. This angle is 31.85. So this vertical distance is 0.5278 s. We earlier found the distance of the point B from the neutral axis as 39.58. So the distance of the centroid of this portion is 39.58 minus half of this, that is 0.2639 s. So here we have written Q, the V is this load and I is IZ dash. So we obtain an expression for tau S. C S is equal to 75 and we get tau C2. We find the stress at B and C due to both loads. Note that the direction of shear stress in this case and for the earlier other load is different. So tau P is given as tau P1 minus tau V2. The direction of the shear stress at the point C for both loads is the same. So tau c is given as tau c1 plus c2. This was the original problem, and these gives the variation of stress in AB and BD. So this is BD. We found out tau P, which is 11, as can be seen in this diagram and this diagram. We also found out tau C, which can be seen in this diagram. The fact that the stress at P is the same serves as a check. Here we have an unequal angle to which load is applied. The dimensions of the unequal angle are given. We are required to find out the variation of stress in the two legs. Such an unequal angle has no axis of symmetry. Here the load is applied at the shear center, so there will be no twisting. To start with, we find out the position of the centroid. The distance of the centroid from the outer edge of the shorter leg is found to be this value. We consider this axis parallel to the outer edge of the shorter leg to be the YY axis. We find the distance of the centroid from the outer edge of the longer leg to be this value. This centroidal axis parallel to the outer edge of the longer leg is designated as the ZZ axis. So here we have plotted the centroid with the YY and the ZZ axis. Next, we determine IY and IZ. After that, we determine IYZ. We consider Y star and Z star, which coincides with the outer sides of the angle, as two axes. Then we find I, Y star, Z star. We find I, Y, Z using the parallel axis theorem. Here A is the area and YC and ZC are these two distances. Here we have obtained the value. Now with IY, IZ and IYZ known, we can find tan 2 theta. We find 2 theta and theta first in radians and then in degrees. Theta is equal to 21.431 degree. So we have the direction of the principal centroidal axis, and now we find the moment of inertia about the two principal centroidal axes. We find I y dash using this equation and I z dash using this equation. We'll resolve the force acting along the two principal centroidal axes and determine the stresses. For that, we need CG and AD. We find these two distances from the center line of the two legs. So this distance minus half the width, and similarly this distance is this distance minus half the width. Now AB is 8.87 tan theta. AC is BC minus AB. So here we have AC. AD is AC cos theta. So here I found AD. EF is 23.87 tan theta, which we have obtained here. CF is EF plus this distance, CG is CF cos theta. So we obtained CG. Here we have resolved the load along the two principal centroidal axes. These two distances are the perpendicular distances of the point C from the two principal centroidal axes. We'll first determine the stresses in the two legs due to this 9.308 kilonewton load. Here we have rotated the angle so that the z dash axis is horizontal and the load acts vertically. We'll find out the stresses in the shorter leg first. As earlier, we considered a portion of length S. The distance of the point C from the edge is 47. So the vertical distance is 47 into cos theta. Subtracting this distance, we get distance of the neutral axis from the lower edge as 26.77 millimeter. This length is S, then the vertical distance is cos theta into S, so 0.931 S. This is the distance of the centroid of this portion from the neutral axis. Q is equal to area into the centroidal distance, so the area is ST and this is the centroidal distance. Tau S is VQ by IT. V here is this load and I is IZ dash, which we obtained earlier. Hence tau S is given by this expression. Here the distance of the edge from the point C is 77. So 77 sine theta is this vertical distance. Subtracting this distance, we get the distance of the neutral axis from the lower edge as 11.16 millimeter. If this distance is S, then the vertical distance is sine theta into S. So the distance of the centroid of this portion from the neutral axis is given by this expression. Q again is area into centroidal distance. Tau S is VQ divided by IT, and V is this load, and I is IZ dash. So we get this expression of tau S for the longer leg. Here we look at the second case. So we find out the stresses due to the load 3.654 kilonewton. Again, the angle has been rotated so that the y dash axis is horizontal and the load is vertical. Let us consider stresses in the longer leg first. The distance from the outer edge to the point C is 77. So the vertical distance is 77 cos theta, which is this value. This is the distance of the neutral axis from C. Subtracting, we get this value. The length of this portion is S, then the vertical distance is cos theta into S. So the distance of the centroid of this portion from the neutral axis is given by this expression. Q is equal to ST into this expression. Tau S is VQ by IT, where V is this load and I is I y dash, which we obtained earlier. So we get this expression as tau as the longer leg. Let us now look at the shorter leg. The distance from the outer edge to the point C is 47. 47 sine theta is this vertical distance. The vertical distance of the neutral axis from C is given by this value. Adding these two, we get 36.15 millimeter. If this length is S, then the vertical distance is sine theta S. The distance of the centroid of this portion from the neutral axis is given by this expression. So Q is equal to ST multiplied by this expression. Tau S is VQ by IT, where V is this load and I is I y dash. So we get tau S for the shorter leg. We can now determine the shear stresses for both the cases or both loads. So for the shorter leg, we add up the expressions and we get this expression for tau S. For the longer leg, the directions of the two cases are different. So we subtract tau S for this case and we end up with the tau S for both loads. This was the original problem, and the stresses have been plotted in the shorter leg and the longer leg. These stresses are for the original problem. For the shorter leg, it has been plotted till 47, and for the longer leg, it has been plotted to 77 millimeter. That is the point C.